All right, today we're going to be talking about our global pressure systems that we have and how they're distributed across the planet. So to start off, we always pick our easiest place to start, which is going to be our equator. And we'll label that one. Not getting a north or south because zero's in the middle. We can also label other key points of latitude lines that we know. South Pole and our North Pole. So if we think about this in a little bit more depth, we know that the equator is the place that gets the most direct heating and direct insolation from the sun. So we would expect temperatures there to be hot, and what does hot air do? Hot air rises. So we're going to draw in some arrows here at the equator that show the air moving away from the surface up towards the top of the troposphere or the tropopause. Once they hit the tropopause, they have to spread out. They can't go through the tropopause and they can't mix with each other here. So what they're going to do is they're going to start spreading out towards the poles. And this is just air in the upper atmosphere at this point that just came from the surface. It rose because of the direct insolation here around the equator. What happens, it doesn't go all the way out to the poles. In an ideal world, it would, but it doesn't on our planet because we're complicated. So ours go to about 30 degrees latitude. Is where the air will kind of stop and start to sink. It'll cool down enough by that point that it'll start to sink down back towards the surface. And in order to complete our convection cell, it's got to end up where it started from. So it'll just continuously flow back towards the equator and heat up as it goes. As it gets closer to the equator, it's being heated more. And then, well, by the time it gets to the equator, it's going to start rising again. So if we've got two parcels of air, two packages of air rising around the equator, we should also have two moving on either side of our key latitude lines. And then they're going to continue to move in this pattern. The cells we've completed thus far, these are called Hadley cells. All right, so the next key line of latitude that we had our tropics, kind of around 30 or so. We've got our Arctic circles in here as well, our Antarctic and our Arctic circles, about 60 degrees. Now, we've got air sinking around the 30s, so it can't go back up towards the equator on the south side of 30 degrees south, so it's going to start going down towards the Antarctic circle, and the one up here is going to start going towards the Arctic circle. Now, there's another dividing line here being these circles, and we can't mix our air up more towards the pole, so we're going to have our air rise. And then to complete our cells, it's going to go back to where it came from. These convection cells are called Ferrel cells. Lastly, the cells down here, we have the same action, the same rising action on either side of that 60. And the air, when it hits the top of the tropopause, it's going to start sinking all the way down towards the poles, where it will sink back towards the surface. And then to complete our cells, we're going to bring it back to where it came from to replace the air that was lifted previously. These cells are called polar cells. So this completes our pressure or circulation cells that we have, but we're not done with the diagram yet. We know that subsiding air or sinking air, based on our upper air highway model that we used, our sinking air back towards the surface is going to create high surface pressure. So we'll mark an H wherever we see sinking air. So here we've got rising air. This is going to create a low pressure system at the surface. Sinking air will create a high pressure. Rising air will create a low. Sinking air will create a high. Rising air will create a relative low. And then we've got our high down here at the South Pole.